Hi there, Rachel Sherman here, and in this video we're going to explore what it means for functions to be one-to-one and onto, as well as learn how to prove statements about functions being one and onto. A function f from a set x to a set y, also known as your domain and codomain, is one-to-one if and only if for all elements x1 and x2, f of x1 is equal to f of x2. Means that x1 must be equal to x2. So in other words, the only way for your output values to be the same is if the input values are also in fact the same. Another name for functions being one-to-one is called injective. So those two things are used interchangeably, and you should be familiar with both. An example of functions which are one-to-one, I mean there are quite a few, and we've already seen some if you've watched the other videos in this series, but take into consideration something like a linear equation, for example. So let's say you have a linear equation where it's defined from the reals to the reals, so your domain and codomain are your real numbers, and even something like f of x equals x. So you have that 45-degree angle there. If you take a look at this, no matter where you go on the line, every single y value has a unique input, so a unique x value that maps to it. So this example on the left here would be something which is one-to-one. On the other hand, if you take into consideration something also defined from the reals to the reals, but let's say you have, as an example, a function, let's say g of x equals x squared. With this parabola, you can see that no matter what you have, let's say you have some arbitrary y value, that there are going to be two different x values which map to that as a y value. So let's call this maybe x1 and x2. So although g of x1 is equal to g of x2, x1 does not equal to x2. And if you were looking for a specific example of this, you could even consider, I don't know, something like when g of x equals 4, right? So that could stem from x1 being negative 2 and x2 being positive 2. So as you can see here, again, one more counterexample as to why this is not injective. Now, if you were to prove statements about things being one-to-one, it's actually a very simple proof. So it all stems around the fact that your assumption is that f of x1 is equal to f of x2. So take for a moment the example f of x being defined by 4x minus 1 for all real numbers x. So we know by looking at this equation and that this is defined over the real number system that this is in fact a linear equation, right? So if you think about the linear equation we just looked at on the previous page, you notice that this will always be that consistent increase, consistent decrease. We don't have to worry about any repeated y values. So we should know already going into this that this is in fact a one-to-one function. So how do we prove that? So our proof starts by saying, okay, well, we've got, I don't know, two real numbers. Let's call them x1 and x2. So let x1 and x2 be real numbers, and that's, as you can see, just defined by the domain given to us up here, such that f of x1 is equal to f of x2. So we've specifically chosen these so they have that special property. What we need to show to prove that this is one-to-one is that the only logical conclusion is that x1 and x2 must actually be the same value. So by substitution, we have 4x1 minus 1 equal to 4x2 minus 1. And if you add 1 to both sides, we're left with 4x1 equals 4x2. Divide both sides by 4. You can see that x1 must equal to x2. There's no ambiguity to the statement. We've shown that any time you have f of x1 equal to f of x2 for these arbitrary real numbers, x1 must also equal x2. Now, if you were to try and show that something is not one-to-one and it's asking for a proof or a counterexample, you can look even at the sake of g of x from earlier. So we said that g of x was equal to x squared, and that was for some real numbers x, so defined over the real number system. Your counterexample could be just like we had described here, right? So it could be the case where x1 and x2 are positive, negative 2. You could have chosen positive, negative 3. You could really give any case. So our counterexample would be let x1 equal 2 or negative 2. I'm going to stay consistent. And x2 equal positive 2. So why is it that this works as a counterexample? Make sure you follow it through. So we know that g of negative 2 is equal to g of positive 2 because 4 is equal to 4, but negative 2 does not equal positive 2. And that would be all you'd have to show to prove that this is incorrect, or not prove, but give a counterexample as to why this is false. Now, one-to-one functions can be a powerful tool, and sometimes I say this with immense caution, is algebraically, a lot of times instructors or teachers will describe this as a horizontal line test instead. Now, if we go back to those sketches that we had, you can see when we drew a horizontal line through g of x, it hit twice. On the other hand, if you draw a horizontal line through this linear equation that we had, so non-parabolic, this linear equation, you can see that it will never cross more than once. So there's some benefits to that, and there are, depending on what you're looking at, reasons why this would be significant. More specifically, we'll look at how one-to-one and onto functions can be applied to cardinality in our next video. So let's take a look at what it means for functions to be onto. Functions are onto if and only if for all y in your codomain, so let's call it maybe codomain y, there exists some x in your domain, we'll just call it domain x to be consistent in how we've been learning this, such that f of x will always equal to y. So in other words, if you give me a y value, I can find the x value that will provide an output of y. Another name for onto is surjective. And now that we've learned both of these terms, if a function is both injective and surjective, we call this bijective. So if it has both of those properties, we can also refer to it as bijective. It's possible for functions to be only injective or only surjective. It could be both. It could be neither. It just completely varies by how the function is, what it's defined as. Now, an example of this, and kind of in layman's terms, if something is surjective, it means that your codomain and your range are equivalent. So in terms of proving something, you can't just prove it by saying, look, the range and the codomain are the same, but in terms of understanding, you're looking for when the range is the same as the codomain. So just like that example we did earlier, the linear equation, it could be any linear equation, right? If this is defined from the reals to the reals, you can see that this will eventually span in the y values, right? It will eventually span all real numbers as well. On the other hand, if you have, let's stick with that same parabolic example that we had earlier. We're close enough, right? So if let's say you have your function g of x equals x squared, and it's defined from the reals to the reals, you can see visually that g of x, in this case, can never be less than 0. And that's problematic, and it means that this would not be surjective because you're talking about the entire real number system. So there's no way for this function to ever span below the x-axis. So you have your case on the left here, which is surjective, and on the right, this is not. Now, for proving these kinds of things, it is as straightforward as we saw before. You're still going to use an algebraic proof, but there's a little bit of prep work involved here. So the goal is to show that you can always find an x that will give you all of the outcomes in your codomain, right? So do your scratch work first. Consider for a moment you want, in this case, f of x to equal some y, and that, we know, has to be some manipulation of 4x minus 1, or whatever the given value is. Solve for x instead, and that will tell you what x will have to be in an arbitrary manner. So by solving here, add 1 over and divide it by 4, we can see that x has to equal y plus 1 over 4. So for my proof, see how we did our scratch work first. Let's say let x equal y plus 1 divided by 4, and we wanted to show how there will always be an x to generate the y's of all of our outcome values, or all of our values in our codomain, if you will. So let's look at f of x, which equals 4x minus 1. Since x is equal to this, we're going to substitute. So let's look at f of y plus 1 over 4. So here we have 4 times y plus 1 over 4 minus 1. Our 4's cancel, so that's equal to y plus 1 minus 1. The 1's cancel, so we've shown that this is equal to y. So in other words, no matter what x is, as long as it meets the criteria, you can find, or no matter what y is, as long as it meets the criteria you've deemed for x, which is y plus 1 over 4, you've shown that it would have to be able to generate those values. Thanks for watching this video. We'll come back in a few minutes here with cardinality. Thanks for watching.